this is a work in progress. I'm just trying to show some preliminary results for something I've been working on recently. So I've been working at the University of Little Rock, or University of Arkansas Little Rock with mainly Mark Siegert. And what we're trying to do is see if there's a simple relation between central dark halo concentration in galaxies and supermassive black hole mass in these galaxies. Okay. So far there have been a few useful relations in order to determine the supermassive black hole mass in the centers of galaxies. There's the Lagrangian relation that gives the black hole mass as related to the bulge mass of a galaxy. There's also the M sigma relation, where the velocity dispersion is also related to the central massive black hole mass. And recently, Mark Siegert has found a relation between the black hole mass and the spiral arm pitch angle of galaxies. So there seems to be some morphological relation between the central massive black hole mass and the actual morphology of these spiral arms. And essentially this came from a previous relation that he's found dealing with the rotation curve shear of spiral galaxies and its relation to the pitch angle. So here we have the shear rate. So the shear rate is just the slope of the rotation curve. And what we see is that there seems to be areas where there's a large shear rate. There is a very small pitch angle relation associated with that. So the shear rate also seems to correlate to a high central mass concentration. Now, whether that's bulge mass and dark halo or whatever, there seems to be a high central mass concentration that affects the pitch angle of spiral galaxies. Okay, so also there seems to be a relation between the dark matter halo mass and the supermassive black hole mass found by PRAOO in 2002. But the interesting thing is that recently there have been found a few late-type galaxies that have little or no bulge, but seem to have AGN in them. So there seems to be a supermassive black hole in these late-type galaxies, but there seems to be no bulge component to these galaxies. So this seems to suggest, along with the rotation curve shear relation, that perhaps the dark matter halo concentration in the centers of these galaxies is actually responsible for the black hole mass in the center of these galaxies. So what we thought about doing was using a relationship found by DiBattista and Selwood in 2000, where fast bars, so bars with a co-rotation to a bar radius of less than 1.4, seem to have a low central dark halo concentration, or low central dark halo density. So what we want to do is we want to see, so let me move on to the next slide. So what we want to do is actually use that relation to test and look into if that relates to the mass of the supermassive black holes in the center of galaxies. Okay, so this is the pitch angle black hole mass relation found by Siegert. So this is for nearby galaxies, and you can see there's a trend here where the high mass galaxies have low pitch angles, or the high supermassive black hole mass galaxies have low pitch angles, and here they have higher pitch angles. And here we have some points, only a few points, but you can see the black hole mass seems to drop off dramatically with increased pitch angle. Now, whether or not this is real, that's why we have two fits here. We have a double polynomial here by equation 2, double power law here by equation 2, and we have a linear fit to fit the majority of the points and maybe leave out these, which may not be entirely accurate. But for the purpose of my project now, I'm actually using the double power law fit for determining the black hole mass. Survey, which is essentially multi-band, using V-band images mostly, whereas it's already been found before that we're trying to actually model these galaxies to figure out the bar pattern speed of these galaxies. So rotation curve. So this is an example for one of the galaxies, NGC 3660. Here we have it's a sticky particle code, which was discussed before, to not basically dynamically kind of shock the system and throw particles out of the grid. So we have basically the bar potential turn on and reach full bar strength after about 2 bar rotations. So the main parameter that we're varying, we can vary all kinds of things like particle size, relative stickiness. So we change the pattern speed so that it essentially ranges, the co-rotation of bar radius essentially ranges, so we're looking at snapshots between 1 and 2 most of the time in increments of 0.1. So the co-rotation radius corresponds to the bar pattern speed. The bar radius we measured basically from the B-band image by fitting elliptical isophotes and looking for basically looking for a minimum in the ellipticity. Comparing the model morphology to the observed B-band morphology and looking for the best fit. This is NGC 3660, which I showed the circular speed curves before. So here, which has a bar feature here, a nice inner ring here, and the models determining whether they're fast or slow bars from these 40 bar galaxies, just to see the general trend. And what I've also noticed when you add the color coding is that we have force calculations. We can get an estimate for the bar strength of. We actually see a trend in bar strength versus central velocity dispersion. So basically, what we're seeing is for a high central velocity dispersion, there's a weak bar. And so for a high velocity dispersion, we see a very tiny pitch angle. So we see a small pitch angle, which would then correspond to a small black hole mass. I'm sorry, a large black hole mass. Bar strength versus pitch angle, and generally you don't see a very good trend for. Maybe there's a trend here between bar strength and pitch angle, whereas the weak bars seem to be very tightly wrapped, and the strong bars seem to be very open. So the question was, is there a connection between central dark halo concentration and supermassive black hole mass? Right now, probably not, but there seem to be conditions involved with that. First of all, we're measuring the pitch angle. So for instance, those upper two galaxies that we saw, those two resonance ring galaxies, we're actually measuring the pitch angle of resonance rings. We're not measuring the pitch angle of the actual spiral pattern. So the black hole mass that corresponds to that may not be entirely accurate. So it's most likely useful to actually get an independent determination of the black hole mass, the central black hole mass of these galaxies, and see if it actually corresponds to the pitch angle that's measured from this relation. On the other hand, if these galaxies actually are fast bars, there are also these pattern speed domains where a fast bar could be outside the inner Lindblad resonance domain and could actually funnel gas all the way to the center, which may actually increase the central black hole mass as well. So it could be one or the other in that case. And so what we also saw is that there seems to be a connection between spiral arm pitch angle and morphological type for fast bars, which also means that then there's a supermassive black hole mass and morphological type relation for these fast bars as well. And then there's maybe a tenuous relation between bar strength and pitch angle or morphological type. And so I'll leave it there.